Hi, this is me again, Wes Thompson. I'm the director of biostatistics for the ABCD study. This is the second part of this four-part lecture. Each part is not long, so don't worry. This part is going to be about missing data analysis. And this is also based on a paper that was published recently by members of the ABCD biostatistics work group. And again, the citation is at the end of the slides that I will share. Let me go ahead and share my screen again. There we go. Okay, so handling missing data. Missing data are pervasive in studies, and they're especially pervasive in longitudinal studies. So longitudinal studies inevitably face missing data due to participant dropout, missed visits, or incomplete responses, or data that don't surpass QC standards. With ABCD's large scale, and here I mean large scale in terms of the number of variables collected, even small percentages mean thousands of data points missing cumulatively across participants. If even like a small percentage of variables are missing, but you have like say 10 variables, that could result in a lot of people omitted from the study or a lot of observations omitted from analysis. As an example, at baseline, only about 50% of ABCD participants had usable data for certain fMRI tasks, compared to 95% with structural MRI data. Thus, missingness can vary widely by measures in ABCD. If we naively analyze only cases with complete data for all variables, that's a very common way of doing this. We may lose a large proportion of the sample. May or may not be an issue. Like, you might, if you go from 12,000 to 8,000, you might still be very well powered. But it could be dramatically smaller than that to a point where power is an issue. And then also as another issue is that like if you delete certain people from your analysis because of missing data and their missingness is related to the associations that you're trying to assess, then that could actually bias the results that you're finding. So here's kind of basically a schematic breakdown of the different types of missingness that can happen. So there's missing completely at random. That means that essentially it's like a coin flip, whether or not the data are observed or not. That means that it's not tied to any covariates or it's not tied to the outcomes. In that case, bias is not an issue. Power may be an issue, but bias is not an issue. However, this is rarely true in practice. And then there's missing at random. Missing this is related only to observed data. That means I know these terminology is slightly confusing, but this is like the standard terminology. So the missing at random actually means that it could be dependent on observed covariates like socioeconomic factors or sociodemographics, or age or whatever. But since you've actually assessed those variables, if you condition on those, conditional on the covariates in your model, the missingness is random. This is actually a very widely used assumption, and can be like more or less justified in many circumstances. And then you finally have missing not at random, and this is where missingness depends on unobserved data. This is the hardest case to handle, and it's actually impossible to prove because you haven't actually observed the data that the missingness depends on. So the only way to address this typically is to do sensitivity analyses to see like what the impact of the missingness could have on your observed associations. So again, we have the missing completely random, missing at random, missing not at random. Missing completely at random doesn't cause bias, but it's really like doesn't really happen that often that you just like that this actually occurs. Missing at random, that's more justifiable, especially if you have a pretty rich covariate set, which ABCD does. But again, it's not completely defensible. I mean, like yeah, like it could be the case that like there's things that you didn't measure that are biasing your missingness in ways that you don't know. And that would be missing not at random. And really the way to address missing not at random is sensitivity analyses. The methods that I go over in the rest of this section are gonna be essentially assuming missing at random. So missing dependent on the covariates you include in your model, they're missing at random. Okay, so what are different ways of handling missingness? Well, there's listwise deletion. That means you just delete rows that have missing data that go into your analysis. This is the simplest thing to do, and it was historically the default in many software packages. For example, if you use the LME function in R, typically what will happen is if there's a missing value, it'll just delete it from your analysis. Um, Drawbacks are that it's inefficient. Inefficient just means you're not using all the information that you have available to you because you're deleting rows in your data set, and it's potentially biased. Um, it could discard valuable partial data, and that reduces sample size power. And the listwise deletion assumes that the missing completely at random. If that's the case, you're not biasing anything, but you are losing power potentially. But if it's not MCAR and you do listwise deletion, then your estimates can be systematically wrong. They can be biased, basically. In ABCD scale data, listwise deletion can drop thousands of participants. So an example is like at baseline, family income was assessed, but a lot of the participants did not answer that. And then also for different imaging variables, like there's different levels of completeness across the different imaging modalities. So MCAR is seldom true. Um, the APA's task force on system inference called simple deduction methods among the worst methods for missing data. I think that's a little, I mean, that's probably true, but I think it's not always indefensible to do this. But you have to be careful about it, and you have to understand that like there's the potential for bias in your results. So, other more modern approaches to missing data include multiple imputation, and this is where you basically replace missing values with plausible guesses from a model, and you do that multiple times. Hence the multiple imputation. The reason why you do it multiple times is because there's essentially some randomness in the imputation, and to account for the randomness that you do it multiple times to see how much the imputed values vary from imputation to imputation and how much of an impact it has on your analysis. So and then you do the analyses and then you combine the results after you're done with the analysis using what's called Rubin's rules. And so it basically takes an average and adds like some kind of Monte Carlo component to the standard error estimates. So that's a kind of a standard way of doing handling missing data when you have the missing at random assumption. Here you include covariates in the model that you think are relevant for the missingness. And if you have a good guess as to what those covariates are, or what they might be, and you include them in your model, then you can dramatically reduce any kind of bias that might result from the missing data. The pros are that it uses all available data, and the uncertainty from the missing data is propagated via the multiple imputation. It's flexible and can handle arbitrary patterns of missingness. One of the cons are that they're computationally intensive, potentially, and can require careful specification of the imputation model. Like not every imputation model is correct, and if you're imputing data according to an incorrect model, that could actually increase your bias as opposed to decreasing your bias. So you need to be careful about the imputation model that you use. Another approach to missing data is propensity score weighting, and this basically uses the observed data to compute the probability that a participant remains in the sample, or that they drop out, or that they have a missing visit or missing values for a specific measure. And then it assigns weights equal to the inverse of that probability to the observation. And so the intuition is that under the missing at random assumption, participants who remain may differ from those who drop out. And then the weighting basically takes underrepresented participants who are still in the data set and upweights them to account for the people that were differentially dropping out at higher rates or missing at higher rates. So the there are baseline weights in ABCD that were incorporated in the data release. This is slightly misleading to put this here, sorry, because those weren't actually incorporated for missing data. They were incorporated to weight the sample back to the U.S. population. So that's in the Heringa and Berglund white paper that's on bioRxiv. But like the more relevant source here is actually the ABCD missing data paper that was published by the biostats work group members. And again, the citation for that is at the end of these slides, and then code for doing the different missing um, data techniques, including weighting, are included as part of that paper. Let's see. Then the next approach, this approach I really like, and though you have to know how to model using structured equation models to implement this one. This is in full information maximum likelihood. Sorry. So instead of filling in data via imputation or weighting or dropping cases, FIML uses all available data by maximizing the likelihood of the model for each observation with its observed portions. So essentially, you include kind of the missingness component as part of the model. So that like so you basically model the missingness as part of your data analysis model. Um, the pros of this are efficient use of the data and no need to create multiple data sets like in multiple imputation. It's often implemented by default in structured equation models and multi-level software for handling missing data. Again, the cons are that it requires correct model specification. I mean, that's a con for all of these different approaches, to be honest. And it can be challenging to do that in very large or complex models. But again, we have code for doing this using the OpenMX package in R. And then it's also possible to do it using M+, if you're an M+ user. Sorry. And so this Lee et al. Paper, again, this is the missing data paper that I mentioned several times. We compared all four approaches, listwise deletion, multiple imputation, weighting, and FIML. And very reassuringly, the results basically produce very similar answers in the examples that we have in the paper. That's not to say that it will always be the case, or that as the study goes along and we have more and more missingness and more dropout, that it will always be the case. But at the current time, it doesn't seem like these different methods actually result in demonstrably different outcomes. And even though listwise deletion is demonstrably the worst, it actually is, not too terrible in a lot of cases with the ABCD data. Um, so um, so again, the issue is we don't know a priori when simple deletion might bias results. It doesn't seem to be the case in the examples that we did that it does. But again, it doesn't mean that it always won't. There's probably going to be cases where listwise deletion will actually result in bias that is not defensible. Here's just a little R snippet using the mice package for multiple imputation. We use Blimp in the paper, and again, we provide code for doing all of the different approaches in the paper. Okay, I'm going to stop here, and I'm going to tackle the next topic in a third recording. Thank you.